Good morning, everyone. Good morning, and welcome to the 7th lecture of the NITheCS SATACS course in category theory. What we did at the last lecture, just before the new year, was to look at the arithmetic in categories. The previous lecture, we observed that we are able to define addition and multiplication in a meaningful way in a category that abstracts the usual addition and multiplication of numbers, so the one in the usual arithmetic. And then at the last lecture, we saw if we could establish some of the basic laws for this more general addition and multiplication in an abstract category without any further axioms on the category. One thing we convinced ourselves was that the distributive law, x times y plus z being equal to x times y plus x times z, that one fails in general. We had an example of a category where this doesn't hold. But we did show that, for instance, the law of commutativity of one of these operations, and by duality, hence, of the other one as well, does hold. However, we need to be careful in interpreting this equality correctly. So multiplication and addition of objects in a category is defined not uniquely. It's not defined uniquely in the sense that when you have two objects, x and y, you can have a diagram that satisfies the definition of product for those two objects. But such diagram doesn't have to be unique. There could be another version of a product. Let's call it product prime, with the projection maps being pi1 prime and pi2 prime, and they need not be the same. The main example of a category through which we introduced the concept of multiplication and addition was the category of sets. And already there we witnessed this behavior. So we could take as one version of the product to be the set of all ordered pairs x, y, where x comes from x and y comes from y. Whereas for another version, we could take, in fact, any set that's bijective to it. For example, we could take the set of ordered pairs yx, where, again, x comes from x and y comes from y. Now, the reason why these two sets are not equal to each other is, of course, that they have possibly different elements, right? The first one has elements where the first coordinate is the one that comes from the set x, whereas the second one has elements where the first coordinate comes from the other set. Of course, when the two sets are equal, they will also be equal to each other, but they don't have to be equal. But even so, if they're equal to each other, even when x equals y, and hence these two are equal to each other, even in that case, we don't going to get a nice equality in the sense that, well, here we certainly have an isomorphism connecting these two objects. You can swap the ordering of the ordered pairs. And these isomorphism makes the triangles that you see here commute. So, for instance, if we go this way and that way, if you compose these two morphisms, that's the same as that morphism, and the same on the other side, and also the same for the other morphism. That equals that, and this equals this. But if I put the identity map here, in the case when x times y and y times x are indeed equal to each other, I can consider the identity morphism here. this will not make those triangles commutative because the pair xy by the identity morphism will be mapped to the same pair xy, and it will be projected to, by this projection, it will be projected to the first. Well, the thing is that here, with this set, we're considering our pi1 prime to be actually pi2, and pi2 prime to be actually pi1, right? So then it will project to the second coordinate, and this one makes it project to the first one, and of course they don't necessarily match with each other. So the summary of this story is that we don't expect x times y to be equal to y times x, but we do expect them to be isomorphic to each other. So we put a little symbol of the equality there to represent isomorphism. And moreover, this isomorphism is a nice one in the sense that it makes the diagram commutative. So if I put an isomorphism here, the one I have in mind over here, that will make this diagram commutative in the sense that this composite will equal that, and the other composite will equal the other one. But we don't have such an isomorphism for the first law. This one fails in a general category, and we had an example discussing why that fails. Okay, so maybe before we move on, are there any questions? Okay. Since it seems like there are no questions, that's fine. So what would be the next step from here? Well, we can consider other laws, like, for instance, the associativity law. That turns out to hold as well. Its proof is can be done in a similar style as the proof of commutativity, but it will be a little bit more involved because now we're dealing with expression of three things, and we can go further in these isomorphisms and establish that each of the sides of the two things, sorry, each of the sides of this law, they are also isomorphic to the product of three things. We defined such a thing before. So product of xi, where I goes from 1 to 3, where x1 is defined as x, x2 is defined as y, and x3 is defined as z. And in fact, that would be a clever way of establishing the isomorphism between these two, namely to establish that this thing over here is isomorphic to the product of the three, and then to establish separately that the product of the three is isomorphic to the other one, but that can be done almost by the same argument. We just swap things around in the proof. So the proof of this is actually very similar to the proof of that. So that's an easy task to then replicate the other proof. And then we can take these two isomorphisms, compose them with each other to get eventually an isomorphism of associativity. Of course, we want to make sure that this will be canonical as well. Canonical in the sense that it will make suitable diagrams commute. And that turns out to be a consequence of the fact that this is canonical and that is canonical. So we're on our 7th lecture, and this is halfway into the course. In the second half, what we're going to do is that we're going to have some tutorial sessions for those who are interested in those. So there is a tutor who will be dedicating their time for this. And I would like to propose that the first exercise to be discussed a little bit to be approached before meeting with the tutor and then afterwards to be discussed together with the tutor is associativity of multiplication. Sipo said I'll mute you, otherwise there's some background noise coming from your side. If you'd like to say something later on, you can just unmute. Okay, so what is the exercise about? Prove that there is a canonical isomorphism between x times y times z and x times y times z. Now, once we establish this for product, because the notion of product is dual to the notion of sum, in the sense that we can get the other notion by reversing the direction of arrows. The proof that works for associativity of product, the same proof with reverse direction of arrows will work for associativity of sum. So we don't have to prove that separately. So this is a useful remark to make here. Associativity of product implies associativity of sum. And of course, the same is true for commutativity, and this is something we observed already last time. We can actually make it a bit more sophisticated, this remark, than just referring to reversing arrows. The thing is that given a category C, I can always consider its dual category. So what is the dual of a category C? The objects are the same, the morphisms are the same also, but they go in the opposite way. So for instance, when I have a morphism from X to Y here, in the dual category, that same morphism F will be a morphism from Y to X. So the actual morphism F, let me use a different color for that. The actual morphism F from X to, from Y to X in, what am I saying here? Yeah, the morphism from Y to X, the same F seen as a morphism in the dual category, the op here stands for opposite. Seeing F as a morphism in this dual category, it is the same F, it's the same thing, but in terms of what it was, in terms of its direction in the category C, it is actually a morphism going from X to Y. So when I have a yellow arrow from Y to X, that means arrow in this category, it means I have a white arrow from X to Y. And so the axioms of a category are invariant under this duality. So when I build this thing out of a category C, it will also be a category. Something interesting happens to composition. I don't remember if we already discussed duality to this extent. Something interesting happens to composition when I have two composable morphisms. In the dual category, the way we can compose them, so in the dual category, a morphism G from Z to Y will be an actual morphism from Y to X in the other category, in the original one, and a morphism F from, sorry, I meant to say from Z to Y. The morphism F from Y to X will be an actual morphism from X to Y in the other category. And I still need to define their composition here, their composite. And that can be defined by taking this composite, but of course this composite now runs from x to z, and here it's reversed from z to x. But we're also going to write it in a different way. We're not going to write gf, we're going to write fg, because so this is our, if you want composition prime, it's composition op rather. So composition in this dual category is defined almost the same way as in the original one. It just swaps the order in which things are composed, and which is an immediate effect of having swapped the directions of arrows. And then associativity of composition automatically carries over, and identity laws also carry over. So we do get C op to be a category. And now if I prove, if I say that x times y times z is isomorphic to x times y times z in every category, if this is my claim, which is the intent of that exercise to establish that, if this is my claim, then I can conclude from this that the same law holds in the opposite of every category, because opposite of a category is still a category, right? So in the opposite C op of every category. So because C op is also a category, this more universal fact that something is true everywhere applies also to these kinds of categories, right? But then by expanding what this means in C op in the language of C, in the language of the original category C, we get exactly the associative law for addition. Any questions on this topic? I hope this is clear. If it is not, please allow yourself to interrupt with a question. Fantastic.
Sorry, may I ask a silly question?
Sure, please.
So as far as I understand, if we have like product of any two objects, then we have product of any finite objects. Can we reverse this as well? So for example, can it happen that we have products of all three objects in the category? What do we expect in that case?
So it is not quite true that having product of two things gives us product of finite things, because the empty thing is not covered by two. When if we know how to do product of two things, it doesn't mean we have product of zero many things. So we might not have a terminal object.
Yeah, I mean not I mean amount of natural numbers one, not like empty. So 2, 3 or something like this.
But then we also need the other one to go back. So if I know that I can take product of three things, I need to take one of them to be look, if we go back with numbers, right? If I know how to, let's say I've got a set of numbers that is closed under multiplication of three numbers. Any three numbers you pick, their product is still in the subset, right? To prove that that set is also closed under multiplication of any two numbers, you will have to, for instance, one way is that you'll have to know that number one is in your subset, right? Because then you can take the third number to be one and hence get product of two things as represented as a product of three things. Do you agree with that?
So yeah, I do agree with the fact that if you have a terminal object, then it can be taken down to product of two objects. but it can happen that we don't have any.
Yeah, but if we don't have a terminal object, then you can have a situation where you have products of three things always, but you don't have products of two things.
Yeah.
Yeah, of course. For instance, I mean, the same example with numbers would work. Let's say we take a category whose objects are, so we take a subcategory of the category of sets whose objects are a two-element set, and the next object is 8-element set. The next one, so each time we multiply by 4, okay? So the next one will be 24-element set. Am I doing this right? I think I'm doing this right. So basically, we take all multiples of 4. No, sorry, or all numbers of the form 4 to the power n. All sets of the sizes of the form 4 to the power n times 2, where n can be any number. Okay. So do we agree that if I take two sets of this size, let's say one is this and the other one is 4 to the power m times 2, what will be their product? Their product will still be of that form because it will be 4 to the power n plus m plus.
Sorry, why do you have
No,
24?
it won't be. Sorry.
Yeah.
So product of two things won't be like that of that form, right? Because product of two such things will be this, which doesn't exist in my subcategory, right? But product of three things will always be there, right? If I take the product of three things, I'll get 4 to the power n plus m plus k plus 1 times 2, right? So take the subcategory of the category of sets, where objects are sets of these sizes, of these kinds of sizes, power of 4 multiplied by 2. Then that category, in that category, you'll be able to form product of any three objects. It will be a set of this size. So if your first object was this size, second this, and third this one, then the product of those three will be object of this size. But you will not be able to take products of two objects. Won't necessarily exist there. I mean, I haven't proved it to you now, but it's not a difficult exercise to prove it. That the product of these two things won't be in the subcategory because it will have to be of this size, but there is nothing of that size in the subcategory. Does that? Are you happy with that, Alexander?
Yeah, totally. What I expected. Thank you.
Okay. But it's an interesting remark you made that products of any finitely many things, as long as it's not empty, they can be built out of products of two by iteratively applying basically this idea. So just like product of three can be built out of products of two things, first multiply y and z and then multiply by x. If we have more of them, we can keep multiplying, and the associativity law will help us to ensure that the way we put brackets doesn't matter. But then we can also establish that that invariant product, where the location of bracket doesn't matter, is actually the same as a product of the same number of things as we have terms in the product. Okay. All right, so we leave establishing of associativity and perhaps other laws, but then the others are actually consequences of the commutativity and associativity. We can leave it up to that exercise that I mentioned, but let us still say a few things about another important law, namely that if you, and let's now move to addition, if you take 0 plus x, that always gives x. So, but in our case, this will be isomorphic to x. And because we know it's commutative, we also will have similarly the other isomorphism. This will be isomorphic to that. Okay, so if I take these up, so 0 here is the initial object. It's the empty sum. And let me remind you what that means. For every other object A, I'll have a unique morphism going into A. And now that I want to establish that 0 plus x is isomorphic to x, I can do so by building x itself as an instance of the sum diagram. So I now need to produce two things here and here. This will be what I usually call iota 1 in the sum diagram. This could be our unique morphism from 0 to x. And this we will take as the identity morphism. And now we can establish that this diagram fulfills the requirements of a sum diagram. So suppose we have any other object C, and suppose we have any two morphisms F and G. We want to produce a unique morphism from X to C, right? What do you think will be the thing we should put in here? So we're looking for a unique morphism H that is unique by the property that H composed with identities G and H composed with iota 1 is equal to F. What do you think is such H? So let's prove existence first.
Well, the text up here suggests that we can take here identity.
Are you saying we should take H to be identity?
Yeah, and C to be X or no, I'm doing something false.
We can't assign a value to C. We must prove something for arbitrary C.
Yeah, you're right.
C is given to us, and then after C is given to us, we need to find H. So C is given to us arbitrarily, F is given to us arbitrarily, G is given arbitrarily, and now we need to find H. And yeah, any suggestions? What could H be? So let me emphasize this distinction of what is given and what is needed to be shown. So it's useful to talk about the logic of mathematical definitions to clarify the structure of the concept, right? So the assumption here is that F, G, and C are arbitrary. And the conclusion we're looking for is that there is exactly one morphism H from X to C for which those two equalities will hold. So among all the H's from X to C, there could be many of them. There's only one, and there is one indeed, that fulfills these two equalities.
Sorry, why do we say that like F is arbitrary?
I don't understand the question.
So isn't it a unique morphism from 0 to C?
Well, in this case, yes. In this case, f happens to be exactly 1 because
Yeah.
0 is initial. But I didn't want to burden my logical structure of the definition of sum, taking
Okay,
into
fine.
account some specialities that happens in the specific situation. We will definitely need those specialities to prove the uniqueness of H, but it's not something that comes from the definition of sum, right? So you're making a good observation here. Even though by definition of sum f, g, and c must be arbitrary, since 0 is initial object, we can already make the conclusion that f must actually equal to iota 1. But what we're looking for is to see what h must be equal to. So we can insert this in the diagram, f equals iota 1.
So we already know that H exists because of our definition of sum in a category, right?
No, we're trying to build the sum in this case. If we knew that this was a sum, then we would know H exists, but we don't know that this is a sum. We are trying to prove it is a sum.
Okay.
So to prove that this is a sum, we want to prove that H exists and is unique. Does that make sense?
Okay, yeah.
So we're trying to establish that if I take two objects, initial, one of them, and another object x, that this diagram will definitely be a sum of 0 and x. So I want to prove that. Hence, I need to check that the definition of sum works in the case of this diagram, right? What does the definition of sum say? If I have another similar diagram, there must be a unique H fulfilling these identities. So that's what I want to prove, that such H exists and is unique.
So can we take just H to be equal to G?
Yes, I think that's the obvious thing to do. In fact, maybe that's the only thing we can do, because the left side of this equality, of course, because we've got identity morphism here, will be equal to H. So basically, this already suggests to us that H must equal G as well. Not just that F must equal iota 1, but H must be equal to G. It does prove for us, that there is at most one H, right? This has forced H to equal G. So there is at most one H. But as easily as this, we can see that there is also at least one H. Why? Because if we do indeed take H equals G, as you were trying to say, as you said, then we do get this, that this holds, and we also do get the other one for free, kind of, because the other composite here, this composite here, G composed with iota 1, will still be a morphism from 0 to C. And we know that any two morphisms from 0 to C are equal to each other because 0 is an initial object. Does this clarify the picture for everybody? So far, I see only one thumbs up. I need 4 of them.
So is G composed with iota 1 equal to identity, like Alexandra was saying? Just because
G
of the
composed with
object.
iota 1 is a morphism from 0 to C, right?
Mm-hmm.
So why would it equal to identity? C might not be the same as 0, right?
C might not be the same. So okay, no, it's fine.
But it is equal to iota 1, right? D is equal to F.
Okay, that's fine. That's fine.
Yeah, because because 0 is initial. So what we have established using this argument is that this is a sum of 0 and x. Now, if I take another sum, some other thing, 0 plus x, let's draw it here as well. If I've got another sum, now I don't remember if we explicitly established or not, but if I have two sums, they will always be isomorphic to each other. I think we did establish that. That if I have two sums, they will be isomorphic to each other. Maybe we only did it implicitly. So if I take another sum, there will be an isomorphism between these because both of them are sums. And hence, that's how I get this isomorphism. So it's an interesting strategy of how to prove this isomorphism. Instead of proving it directly, we first prove that x itself also is a sum. Then we know that this, well, by the look of it, also is a sum. And when we have two sums, we use the fact that two sums will always be isomorphic to each other. I want us to focus more now on this idea that two sums are always isomorphic to each other, because actually it turns out that this is a special case of the fact that two initial objects are always isomorphic to each other. So we can actually represent sum of two things, and even of arbitrarily many things, itself as an empty sum in a different category, though. So let's look at this slightly controversial idea. Every sum in a category C can be viewed as the empty sum in a special category, in a different category that we're going to artificially make for this purpose. Now we are really going outside of the realm of traditional arithmetic, where there is nothing like this that holds there, and intuitively it is also very, very strange thing to say that every sum of numbers is zero in a different category, because there are no different categories there. In a traditional arithmetic, we only deal with natural numbers. Okay, so we're going to unpack this in a special case where I is a two-element set. So when we take sum of two objects. Let us illustrate this for sums of pairs of objects. That is when the cardinality of I is 2. So I've got my sum here, x, y, and x plus y. And let's again recall the definition of a sum. A sum is a diagram of this form, such that for any other diagram of a similar form, right, with f and g instead of iota 1 and iota 2, there exists unique morphism from x plus y to c, making the two triangles commutative. We're not saying here that there is only one morphism between x plus y and c. We're saying among all the morphisms from x plus y to c, there is exactly one that makes this commutative and also that commutative. So that makes h composed with iota 1 equal f, and it makes H composed with iota 2 equal G. It is unique by those two properties. Now let's compare this with the definition of an initial object. What does an initial object do? If I've got a category, an initial object in it, let's say an object A is initial when for every other object B, there exists unique morphism from A to B, right? So clearly where this lacks to be the same concept as that of an initial object is that we're imposing some restrictions on H here, right? We're not just saying that there is exactly one morphism from X plus Y to C. We're saying that there is exactly one morphism with the property of these two triangles being commutative, right? Whereas here, we are saying there is only one morphism from A to B. So in a very direct way, we can't really say that initial object is the same as a sum. But what if we can change our category? So here, on the left side, we are working in a certain category C. Now, on the right side, can we design a new category in such a way that being initial in this right-hand side category will correspond to being a sum in the left-hand side category? What do you think?
It should be initial object.
Sorry?
So what was the question again?
So can we build a new category out of C?
Yeah.
So that something that's initial in that category will be the same as the thing that's a sum in our category, a sum of specifically of X and Y in our category C. So I want to be able to write that X plus Y in C, so this sum is taken in C, is the same as, is equals to some initial object in some different category made out of X and Y. So let me put X and Y as subscripts of C.
So I think the same is actually true for any construction in categories. Like every construction in category is a terminal object in some certain category. No?
Yes, the same is true for all universal constructions, indeed. But this is now the first time we are, I mean, the sum and product are the first examples of universal constructions we're exploring here. So that's why we're asking the question for the specific case. But do you know how to produce such a category in this specific case? So it's really an interesting problem to reflect on. The solution kind of comes out very easily once we think deeply enough about it. So we want our A to be the same as this entire thing, right? At the end of the day, that's what we want. So now I need to build this other category, 0x. Sorry, why did I say 0xy? I should have said here cxy. I should build this other category. And perhaps I want the objects of that category, because A is one of the objects. Perhaps I want the objects of that category to look similar to these kinds of diagrams, because at the end of the day, I want my initial object there to be equal to something like that. So let's declare objects of this new category we're trying to build to be diagrams of this form. Are diagrams. So when I write object A, what I mean by that is a certain diagram. Let's call it, let's put there A underline, and we can put here iota 1a and iota 2a. So we can define objects of this category to be diagrams of this kind, so that at least there is a kind of match of the form, right? If we say that this is so, then we can maybe imagine that indeed it is possible that A will be equal to this, because this will be one of the objects in the category. So potentially it will be equal to A. Well, in the similar vein, then B, because it's an object in the same category, will also have the same form. And we could think of it to be the other diagram, right? So really here we have a general form of objects of this new category, right? Because we say arbitrary C, F, and G. We're basically saying arbitrary diagram of this shape. That's not how we agreed to write objects of the other category. So let me use this, the notation we agreed to use. But up to change of names of variables, we can really think of this to be the same kind of thing as this one, right? In both cases, here we've got an arbitrary object, and here we have two arbitrary morphisms going into that object from X and Y respectively. All good. So we now know what objects are in this category. What about morphisms? And we have to be careful here because we have to define morphisms in such a way that uniqueness of this morphism must correspond to uniqueness of something here making those equalities hold. So how shall we define morphism from this diagram to that diagram?
So I would suggest it to be like triple of morphisms such that a diagram commits, maybe.
Well, if we define it that way,
This is one
if
way
we
to do
define it as a triple of morphisms, which seems to be a natural thing to do, let's say H0, H1, H2, then the problem is that definitely, well, I mean, so how are we going to ensure that this works? Because this is kind of a special case of this, but only when we take H0 and H2 to be identity morphisms, right? I can expand my diagram on the left side. I can rewrite it in a slightly different way. I can put my iota 1 here, iota 2 here, F and G. And then I can put these equality signs here representing identity morphisms. And now saying that this composite equals that is the same as saying that this composite equals this composite, because here we have identity morphisms, so it doesn't change the F. So in principle, I could then take this inner side completely out. And then get something similar to what you wanted. I can also further take these ones out. So now my definition of sum, it's the same definition, but now the picture I use is different, says that going this way must match going that way, where here by identity morphisms, sorry, by equality signs, we mean the identity morphisms. So this is the identity morphism from X to X, and this is the identity morphism from Y to Y. But then if we do this matching, then we notice that on the right-hand side, we can't have an arbitrary H0 and H2, right? Because then the right-hand side condition will be different to the left-hand side condition. So I hope that makes what I'm going to say next clear. So instead of what you suggested, let's propose that what you said is true, but in the special case when here we have identity of X and here we have identity of Y. So in other words, and then I'm going to call this H underscore. So in other words, a morphism from A to B is not given by a triple of morphisms because the first two are always fixed. It's simply given by a morphism from A underline B to B underline. And we can call it the same name. We can still call it H. For the purposes of formality, we write it as H underline. We can really think of it as H. Well, okay, so we've built objects and morphisms in this new category. We still need to build composition. But let's not worry about composition for now. Let's come back to it a bit later. Because the definition of initial object actually doesn't require for us to know how composition is defined, right? And we need composition later to establish that two initial objects are isomorphic to each other. So if we agree that objects in this category C with subscripts X and Y, objects are diagrams of this form with a fixed X and a fixed Y. So this is one object, this is another object, and there are many others, as many as there are these kinds of diagrams with the left side being X and the right side being Y. We agree that objects are these, and we agree that morphism from one such diagram to another such diagram is given by a morphism between the middle parts of the diagram, making the diagram commute. In other words, making that composed with iota 1 equal the other iota 1, and composed with iota 2 equal the other iota 2. Since I've got identity morphisms here, that's what the commutativity of the diagram reduces to, right? So if we agree on all of this, then to say that I've got an initial object in this category is to say that I've got a certain diagram of this form, such that for any other diagram of that form, there exists unique H making these two whole, which is exactly the same definition as what I have on this left side. Does that make sense to you, Okotisa?
Yes, it does, but of course the question is, why do we have to abstract further to something? Is there something that you can see by doing this? Why do you do this?
That's a very good question. The reason why we want to do this is to reduce the fact that the sum of two objects is unique up to isomorphism, to reduce that fact to the fact that the initial object is unique up to isomorphism. So we're coming to that now. Before we come to that, I also need to define composition in this new category that I've built. So if I have three objects now, let me actually, yeah, let's keep the same picture. Let's say I've got three objects. One is A, the other one is B. And let the third object be C. And say I've got a morphism F from A to B. So this will be given by the morphism from A underscore to B underscore. And then G given by morphism from B underline to C underline, making these diagrams commute. Now I need to define how I compose these two things. I need to define the composite. So what should be G composed with F? Well, the diagram for that will be, so I've got my first object. The composite forgets the middle object, right? I've got my first object. I've got my last object. And I'm looking for something here from A underline to C underline. And what do you think we should take that to be? So I'm trying to define composition in this new category, right? So we're defining composition in the category C, X, Y. How do you think I should define? Yeah.
Is it the obvious G underline? Did you mean to
Yeah.
say G underline?
Yeah, exactly.
Composed with F underline.
Yeah, well done. So the underline of the composite, which defines the composite, is going to be G underline composed with F underline. And of course, because this commutes and that commutes, this thing will commute, right? I mean, geometrically, it's very easy to see. Commuting means that going this way is the same as that. And then here, going this way is the same as that. So going all together this way, which is this what we have here, will be the same as that. How? Well, this way will be the same as this way. And then that way will be the same as this way. So first I change this part to that part, right? So this way gives me the same as that way. And then I change that one, this part, with this one. So that is the same as that. And the same will be on the other side. If this commutes and that commutes, then I'll have something commuting there as well. So that I needed to check this to confirm that this thing is indeed a morphism in our category. It satisfies the definition of being a morphism. So algebraically, we can write this out by saying that, okay, in the first case, we needed to have F lower bar composed with iota 1A equaling iota 1B. And here we needed to have G lower bar composed with iota 1B equaling iota 1C. And on the other side, I need to ensure that G composed with F lower bar composed with iota 1A equals iota 1C. And I can do this step by step, right? First, I expand this to how it was defined. So this will be G lower bar, F lower bar, that composed with iota 1A. And then I can use associativity of composition to say that this is the same as this. And then here I can use that equals iota 1B. And then here finally I can use that equals iota 1C. So we get the result on the left side. The yellow part is now confirmed, and the blue part can be confirmed in the same way. So this defines composition in CXY. So just by defining composition by the formula, basically, this is the formula that defines composition. And once composition is defined like this, it is easy to see that all the laws that we want hold. For instance, associativity law holds. Why? Well, H composed with G and then composed with F in this new category equals what? Well, this one was defined as H composed with G, right? And by this definition of the other composite, it's the same as that underscore or underline composed with F underline, right? And then by definition of what are we doing here? Yeah, first let's now, so we've computed this middle part, right? Okay, great. But there's something strange going on here. No, nothing is strange here. So what will be this expression? Well, that's my morphism, right? And that's its underline. So isn't that the same as this? If I have two morphisms U and V, I first take their composite, V composed with U, and then I take their underline.
So it's
What is
not
that?
like double, it's not like double conjugation in complex numbers where underline just gives you, that doesn't happen here.
No, that doesn't happen, I think. But I'm still, maybe you're right. Let me think about this. So I'm a bit confused now. I think I wasn't expecting to get that expression there. So what do we have here? Here we have a morphism inside the category C, right? Every time I put underline, I'm switching back to the older category C. So here I've got that morphism inside category C. And then I'm composing, maybe, I think it will be more illustrative if we incorporate underline notation a bit later. So let's first write this in the form of H composed inside the category C, X, Y. So this is the composition of that category with G, and then composed in the same category with F. So what is that equal to? This expression is given by H underline composed with G underline in the original category C, right? What about the other one? The other one is there is something strange going on here because here H, G, and F are morphisms in the category. So H, G, and F are morphisms in this new category that we built, right? H underline and G underline are morphisms in C. Yeah. So these are morphisms in C. I think the problem is with the formula, with our formula. This is where we introduce the problem. We said that we want to define this to be the thing whose underline is given this way. Yeah. So the composite here is defined as the thing whose underline is G underline composed with F underline. So let's keep that in mind. Does somebody want to help me out here? I'm stuck. There is this syndrome sometimes when you lecture, you blank out, and I think I've got it right now.
So what exactly are we wishing to prove right now?
We want to establish that the composition we defined. It's always a good question to ask when you're stuck. We want to prove that the composition we defined here is associative. So let us be precise in this notation. So this composition is defined in the new category, in the category CXY, and is defined this way, that its underline is G underline composed in the usual way in the category C with F underline. So then we want to show that this will equal to the same expression with the brackets rearranged. And okay, so we begin by like this. So what is this equal to? This equals, by the definition of composition in the new category, it's H underline composed with G underline. And now, no, that's not true. That is the mistake I'm making. Okay, so it was a good question to ask Alessandra. So this is not equal to that. That's the mistake I'm making. The underline of that is equal to that. So let's go back here. Remember, this thing itself is not equal to G underline composed with F underline. The underline of that is equal to that, right? So we can't first simplify the inside part. We actually don't know how to simplify the inside part yet. We first want to simplify the outside part. So something composed with something, and even that we can't simplify, but what we can do is to simplify its underline. So we first are going to establish what happens when I apply the underline operation to this expression. The underline of that thing is going to be what? It's going to be the underline of the first term composed in the usual way with the underline of the second term. Then the underline of the first term is the underline of H composed with the usual way with the underline of G. Then here we use associativity of composition in the category C. So thanks, Alexander. I was able to get unstuck. I hope this is also clear what we're doing for everybody else, but we'll come back to it if it is not. So now I can use associativity in the category C. And this will give us that, right? Which itself in turn equals, so that is what is that? That is H composed in this category with that object, with that morphism underline. So we only get that this composite, we don't yet get that this composite equals that composite. We get instead that its underline equals to the underline of the other. So coming back here, we have a situation where actually, let me redraw the diagram. So we've got a situation where these morphisms are from A to C, right? Not from A to C, sorry. The F, G, and H, there were three of them. So we added a third one here. Let's say H is from C to D. So they're morphisms from A to D. So from A to D, I have two morphisms. One is one is H composed with G composed with F, and the other is H composed with G composed with F. And what I was able to establish is that the underlines of these are equal to each other. So the underline of the first equals the underline of the second. Why does this imply that these morphisms are also equal to each other? So this requires us to go back to how we define morphism, right? What did we say about that? So what is a morphism f from A to B. We defined it as a morphism from A underline to B underline, right? When we say this, what we have in mind is that there is a one-to-one correspondence between morphisms from A to B and morphisms from A underline to B underline, just like there is one-to-one correspondence between objects of the other category and objects of the older category. Well, actually, not quite so, right? Objects of the new category correspond to diagrams in the old category. So by saying that there is a one-to-one correspondence, of course, we do mean that if f underline happens to equal to f prime underline, that it must imply that f equals f prime. Which will give what we want here. So we will get that these two are equal because their underlines are the same. So one way to kind of simplify this technical syntactical thing obstacle we're getting here is to simply define a morphism from A to B to be exactly the morphism from A lower to B, A underline to B underline. So basically to define F equal F underline. That would be one way of simplifying things. But we could also define it in any way. So we could, for instance, define F to be a triple, as Alexander was originally saying, consisting of three things, identity X, F, and identity Y. But even that might not be satisfactory because this triple doesn't remember what the domain and codomain are. We might want to make it even more sophisticated. We might want to make it a whole system where the rest of the things in the system are specifying these morphisms and those morphisms, just to keep track of what the domain of F is and what the codomain of F is. But if we don't care about that, then the simplest way is just to define F to be the same as its underline. I hope I didn't confuse you. Does that make sense? Or if not, do ask a question. Okay, fantastic. And all right, so we established the associativity law, but in the same way, we can also establish the identity law. So what will be identity morphisms in our category, in our new category? Let's say I've got something like this. If I take two copies of that, so two identical copies of the same thing, right? So that corresponds to having object A and itself. Then we can define the identity morphism from we can select the identity morphism in this new category CX, Y to be the thing whose underline is the actual identity morphism from A underline to A underline. So it's the identity morphism of A underline. So the underline of that is equal to the identity morphism of A underline. And using the same algebra as before, we can get convinced that this will indeed be identity morphisms in this new category. So we've now built fully the category CXY. And in this category CXY, we can apply the following general theorem. Any two objects in a category. So now I'm coming back to your original question, Aquatis, about the usefulness of what we're doing. Any two objects in a category, any two initial objects in a category are isomorphic. This is a general fact. It holds in every category, and it's actually very easy to confirm that, right? So if I've got two initial objects, I1 and I2, because I1 is initial, I've got a unique morphism here, let's say F. Because I2 is initial, I've got a unique morphism the other way. Then I can compose them. I can consider the composite GF, and on this side, FG. But because I1 was initial, GF would be the same as identity of I1, and FG would be the same as identity of I2. Similarly, because I2 is initial. So just reminding you the argument we use for proving that two initial objects are isomorphic. It's a very simple argument, right? This is an extremely simple argument. So you got unique morphisms in each direction, and they compose to exactly identity morphisms because there's also unique morphism looping from initial object to itself. Now, this very simple fact can now be applied to this complicated category we constructed. So the corollary of this theorem is that any two initial objects in this kind of category are isomorphic. But what are initial objects in this more complicated category? Well, they are sums inside the original ones, right? So we have one step of deriving corollary from this, and the corollary of this is that if I have one possible sum of x and y, and if I have another one, they will always be isomorphic to each other. So this will be true for any, and they will be canonically isomorphic because this isomorphism from the previous corollary will exist in our constructed category, and so it will satisfy this commutativity of those triangles that we want the canonical isomorphism to satisfy for any two objects in a category. And moreover, we can also generalize this not just to sum of two things, but of sum of arbitrarily many things. So we can say that any two sums of as many objects as we want will always be isomorphic to each other as a simple consequence of a simple fact that two initial objects are isomorphic. This fact itself is less simple. If you remember how we established it, we had more complicated diagrams than the one we need to establish that initial objects are always isomorphic. Does that answer your question satisfactorily, Akotisa?
Yeah, it does. I think, yeah, the reasoning is much more important than the result. So yes.
Yeah. So now this fact that two initial objects are isomorphic to each other becomes quite a fundamental fact. In fact, in a half joking way, but half serious way, I like to think of this theorem as the fundamental theorem of mathematics. And the reason I like to think of that is that it turns out that many mathematical constructions, and this is not just in abstract mathematics, things we do with numbers, like construction of complex numbers, for instance, and I'll illustrate to you this in a moment. Many of these constructions can be represented as being initial objects in a certain category. But now, you need to be sure that this doesn't give you too much of a variation of what kind of things you could have built. You need to be sure that if you have two ways of representing something as an initial object, or you have two different initial objects, that they're actually the same thing in the sense that they're isomorphic to each other. So that allows you to be certain that your definition of something as an initial object is good enough, that it actually gives you something unique up to an isomorphism, but that's good enough. And to illustrate this, let me give two examples of how we can apply this theorem to two important number systems. One will be the natural number system, representing a natural number system as an initial object in a certain category. It will be a different one to the one we constructed here for the sum. And the other will be the complex number system. So for the natural number system, we can consider the following category. Objects in this category are what I like to call counting systems. This is an idea that was first introduced by Richard Dedekind. So Dedekind didn't do much category theory explicitly, but implicitly he did, in the sense that he wanted to find a uniform and unified language for mathematics. And then this approach to unified language, especially using the language of sets as a unified language, was continued further by NIThe, who was able to drive back then a new field called abstract algebra, but now it's a very standard thing, but the foundations of this subject were laid down by Dedekind and NIThe's commitment to unification. And then these ideas of unification and common language were somehow influenced MacLean, who was attending some of the lectures of NIThe. And in one of his writings about who could have invented category theory, if not him and Heidelberg, he says that one possible candidate would have been NIThe. So, so we're going back now to ideas of Dedekind about the natural number system and the induction axiom, which is another way of looking at it, but there is also a different approach to it using the recursion law, which Dedekind pointed out in this explicit way. But we will now see that definition of recursion is actually stating that something is an initial object. Of course, he didn't have the language to state that. This was later observed in this language by William Lovier, who is a prominent category theorist. He developed many fundamental ideas of the subject. So objects are counting systems. What are counting systems? So imagine we want to have a system of counting things, and we don't want to yet write down all the axioms that the system should satisfy, because they're complicated. We want to simplify life. So what are the minimal requirements from a counting system? What does counting do? If we think about the process of counting, we've got a set X. These are the names or figures or tokens, so things we count with. If you go on a flight, the stewardess will have a special device, a clicker in her hand, and it is not to detonate a bomb. It is to count how many passengers there are on the plane. But in order for not to make a mistake in counting, instead of doing it in her mind, 1, 2, 3, 4, what she does is she clicks every time she spots a passenger sitting in their seat. And then, of course, the numbers are shown on the display. So whatever is shown on the display are the elements of the X. Or in a more primitive world where we haven't invented numbers yet, we can count things by drawing these vertical bars on a piece of rock or something like that, right? Every language has its own set X. In English, it's called 1, 2, 3, 4, 5. In French, it's called 1, 2, 3, 4, and so on. In Georgian, it's called Ertiori, Sami, Otri, and so on. So these are the figures that we will use for counting. And then we need to have a special figure, the one that we use as a starting point for counting. And it's convenient to think of it as 0. So if I want to count how many elephants I've got in my house, because I have none, I do my counting like this. I first say 0, then I start looking for them. And if I can't find anything, then I'll stop at 0. So we can think of 0 as being the starting point of counting. And then I also need a function from x to x, which tells me what is the next word I use after the previous one. So this is the successor function. 0 is mapped to 1. So after I said 0, the next one, when I spot an elephant, I should say 1. After I've said 1, when I spot another elephant, and if I do, I should say 2, and so on. So S is the function that tells me how do I advance in my counting. Now, let us call a counting system any triple of this sort, so any set X whatsoever, any distinguished element in it, and any function from X to X. You might think, okay, but this is weird. Why would anybody use arbitrary such system? And let me actually convince you that people do. When I was at school in Georgia, when I was somewhere in grade 4 maybe, or grade 5, we had a very, very good teacher of the Georgian language. And she taught us that in the ancient times, Georgians used to use Georgian letters for representing numbers. So for instance, 1 would be represented by maybe letter A and so on, in some sense similarly to Roman numerals, to how Romans used Latin letters for representing numbers. But then something interesting happened. So there was this letter which no longer exists in the Georgian language. It was called Upchgu. It's written like this. It kind of reminds one of the infinity symbol. And that letter used to represent a very large number. I think it was 10,000, if I'm not mistaken. But what is even more interesting is that in this counting system, there was no number after 10,000. So if you had something more than 10,000, you would still have 10,000. But of course, it wasn't called 10,000, it was called many. And I mean, it kind of makes sense in real life, right? So how much do we want to count things? When I look at the sky, I don't go 1, 2, 3, 4, 5. I say there are many stars, right? I don't really go beyond many. And so that's the idea that's represented here. So one possible counting system is where I've got X to be a set of numbers, let's say from 0 to some very large number, maybe 10,000. And S of X is defined as X plus 1 when X is strictly less than 10,000. But when it is equal to 10,000, it is S of X is still 10,000. And it's not just ancient Georgians, but there are also many other cultures which actually use this counting system in their everyday life. There is another one that I've observed that children use when you first teach them how to count. Let's say you've got a kid and you teach them how to count, and first you will teach them how to count, let's say, up to 4. So this is one counting system. Here's another one. Very often what happens, because at that point you've taught the child how to count at a very early stage where you've just made them memorize the names of numbers. You go, okay, maybe it's actually 5, not 4. You go 1, 2, 3, 4, 5, okay? And then if you ask the child to continue counting, what happens, and that's something I've actually observed, is that the child goes like this: 1, 2, 3, 4, 5, and then it goes back to 1, 2, 3, 4, 5. So it thinks that after 5 comes 1 because it stopped, 5 has stopped, so now we have to go back to the beginning. This is very similar to how we count time, right? After 12 hours, we have the first hour again, and second hour, hour 3, and so on, hour 12, and then again hour 1. So it's not very far from we keep track of time in a way. So there, S of X is equal to X plus 1 when X is less than 5, and is equal to, it's kind of modular counting, right? It's equal to 0 when X is equal to 5. Okay. Now you might think, okay, where are we going with this? Well, I want to give 2 more examples of a counting system, just to convince you that there are many of them before we define morphisms between them. So this is another counting system. Let me separate them. We had 2 counting systems so far. A third one.
So sorry, are there like any properties that a counting system should possess, or
No
no?
properties. No,
Not at all?
not at all.
Oh, okay.
So in our most general definition, we have no properties. The third one would be 0, a counting system where objects are names of numbers in the English language. 0, 1, 2, 3, and so on. And 0 is defined as 0, and S of X is defined as next number after X. And the fourth one would be the same thing, but with different names for numbers. Let's say I'm writing in Georgian. Noli, Erti, Ori, Sami, and so on. And so Noli is Georgian word for, sometimes it's also called Nuli, is for 0. And the S of a number is the Georgian name for the next number after X. Name for the next number after X. And of course, every single language that people speak will produce their own counting system where the actual elements are the names of those numbers. And they will be maybe more natural than these first 2 examples, which are a bit strange counting systems. And there will be even more stranger things if we really don't require any axioms, and we don't for the time being. And now let's define a morphism. So we want to build a category out of this because we want to do a magical thing. So we're first going to build a category out of this. We're going to define morphisms and their composition. And then we're going to look at what is the initial object in the category. And it will turn out that initial object in this category will be exactly the natural number system as we know it. But of course, it's defined up to isomorphism, for instance, because both of these, this one and that one, they will be isomorphic to each other, but not equal to each other. So what is a morphism of counting systems? And really, you need to think of this as a translation between languages. Let's say I've got 2 languages for counting, the X language and the Y language. And the X language has the special element, the 0 element, which I can think of it as a map from a 1-element set to X that picks out the 0, the number 0. I mean, by number 0, I mean the thing in the triple. So remember that the counting system was defined as a triple, X, 0, and S. And maybe for the sake of this notation, I'm going to call this thing with primes. So x prime and 0 prime. X prime, 0 prime, and s prime. So this is my successor function here in the first counting system, and this is my successor function in the second one. So I've got two languages, the x language and the x prime language. Now, what is a translation from one language to another? Well, a translation assigns to every word in the first language, it assigns a word in the second language, right? So that would be a function. Let's call it t.
Sorry for interrupting. So
Yes.
as I understand, S and S primes, they stand for successor function.
Yes.
What do like 0 and 0 prime stand for?
The initial number in each case.
Initial number.
Yeah, the starting number.
Okay, fine. Thanks.
So if we're using the Georgian and the English counting systems, then 0 here is the word 0, and the 0 prime there is the word noli. So whatever the starting point of my counting is in that counting system, that's what 0 stands for. Maybe I shouldn't have called it 0. Maybe I should have called it something like E or something like this, but now it's too late. So what is a translation from one language to another? It assigns to every word in one language another word, right? Okay, so Okwatisa, in your language, how do you translate in your home language? How do you translate 0? Do you have a name for 0?
I think it's I'm not sure if it's directly or a translation from Afrikaans or something, but Noto. So
would you spell it like this? N-8-O-T-O.
yeah, sorry, yes, like that.
How would you translate 1?
T, so that would be NTHIHIL. Yes. HI, yes.
How would you translate 2?
BILI, so MBILI.
Fantastic. Now, in this process of translation, one thing we want to ensure is that if and so what is the name of that language?
Venda. Yes, Venda.
So we've got Venda language here and we've got English language here. So in this process of translation, we want to make sure that if an Englishman says a number, right, and then advances by 1, now it shouldn't matter when was the translation done. Was it done before he advanced? So first we translated the number he said to Venda, and then we advanced by 1 in the Venda language. That should give us the same result as translating the advanced number from the English language, right? So if I let's say 0, I'm counting something, and maybe I'm actually counting elephants in a park or something. So I've got number 0, and so this person who speaks English, he looks around him, and he wants to start counting how many elephants there are around him, and he begins with number 0 before even looking at the elephants. There's 0, and then he spots one elephant and says 1, right? So he advanced by 1. Now the correspondence between languages should be such that if we first translate 0 to Noto, and then we advance in the Venda language, so first we do this, and then we advance to get to T, I should actually get the same result as first advancing in the English language and then translating that in the Venda language. And do you agree that we will have this correspondence, Okwatisa?
Yes, it will be the same.
Now, this rule that I expressed here is actually a commutative diagram. We're saying that first applying the successor function in the first language, in the X language, and then applying the translation function should be the same as first translating and then applying the successor function. in the other language. But the same will work for the starting number. Of course, the starting number in the English language should translate to the starting number in Venda. 0 should translate to Noto. So we have another commutative diagram where we can draw here identity map from the singleton to itself. So this is the identity map of the singleton. It maps star to star. And so first applying 0 means mapping star to 0, then translating it, t of 0. That must be the same as first applying this identity map, which just gives us star, and then taking the 0 in the other language, which would have been 0 prime. That must be equal to t of 0. So the two rules we get is that firstly, t of 0 must equal 0 prime, and secondly, t composed with s must equal s prime composed with t. Or if I write it with elements, t of s of x must equal s prime of t of x. So this is how morphisms are defined between counting systems. Now there is something very familiar about these, or maybe not, but maybe it is to you, about these two rules. Let me show you one thing that will trigger this familiarity in you. So how can we define addition of numbers recursively? I could define addition of numbers like this. I could say n plus 1, define that to be n plus m plus 1. So this defines how to add to n the next number in terms of adding the previous one, but also I should say how to add to n number 0 to know how to begin adding. This will be another law. So we can express this definition of addition by recursion. I can express this as a morphism from which triple to which triple. So let me make a picture here. So let's choose my triple the following way. Let x prime, so let x, first of all, be this natural number system with its usual successor function where x maps to x plus 1, and 0 is the usual number 0. Let's choose x prime to be, again, the natural number system, but a strange one in which we start counting not from 0, but we start counting from n. Okay? If this is so, then having a translation from this system to that system means having a function from t function from n to n, satisfying these two laws is what? So the first law becomes t of s of x. But what is s of x? S of x is x plus 1, right? T of x plus 1. And let me write, instead of x, let me write m. T of m plus 1 equals, okay, sorry, I didn't tell you what s prime should be, but s prime, I will pick it to be the same as s. So it's again adding 1. So so what is m plus 1? M plus 1 is successor of some m, right? And so t of that must equal the successor, in other words, something plus 1. And what is that thing? That's t of x. So t of m plus 1. And this rule becomes t of 0 must equal n, right? Okay. Now, do you see that these two equalities are basically the same as those two, where my t function, I can think of it as adding something to x, adding n specifically to x. So here I have T of m plus 1, and here I have T of m plus 1. So this recursive definition of addition, so in other words, the definition of adding, so what is this function? It's a function of adding n to a number, right? This definition of adding n can be seen as a translation from the triple n 0s to the triple n small n and then the same s. So it's a morphism in the category. But how many ways can we add n? Those of you who are familiar with mathematical recursion know quite well that when I have a system of formulas like this, so the first one must hold for every m, right? This defines T uniquely. Indeed, there is only one way of adding n, right? It's given by the usual addition operation. So what I'm saying basically is that there is exactly one morphism from here to there. And that morphism is given by adding n. In fact, what I'm hinting on now is that the usual natural number system is an initial object in this category we can build where morphisms are defined by this picture of orange arrows. Let's convince that this is so. Well, if I have any other counting system, I'm looking for a unique T such that these equalities hold, right? Will such T be unique? Well, that's exactly the principle of recursion. The principle of recursion tells you that there is always unique T that makes these equalities hold. Because look at this. We're saying what T of 0 is, and we're saying what T of every next number is in terms of T of the previous number. And we know that if we do this, then it will define T uniquely, right? Because if we know what T of 0 is, what will be T of 1? Well, we said that T of every next number must be the next after T of the previous, right? So if I believe in these laws, this one and the other one with a 0, then T of 0 must be 0 prime, right? That's all, given. What is T of 1? T of 1 must be T of successor of 0, because 1 is successor of 0. But then by this formula, that must be this other kind of successor, whatever that function s prime is, of T of 0. But we already know that T of 0 must be 0 prime, so that must be s prime of 0 prime. Then T of 2 must be T of successor of 1, because 2 is a successor of 1. And that must be s prime of T of 0. Sorry, that must be s prime of, we already know that T of successor, sorry, that must be s prime of T of 1, right? And we already know what T of 1 is. T of 1 is this. It must be s prime of 0 prime. And it will go on like this. In general, we'll have that T of n must be, or let me call it rather m, must be s prime composed with itself m many times applied to 0 prime. Does such T exist? Of course it does. We can define it this way. Well, if I really want to prove it exists, I will have to go back to Dedekind's theorem. But how do I prove Dedekind's theorem? It turns out you can prove existence of T by using mathematical induction and a bit of set theory. So you can actually prove that such T exists if you want to prove rigorously, but intuitively it's clear it exists. Is it unique? Well, of course it's unique. Here's the formula defining it. It must satisfy this formula, and the right-hand side is uniquely determined by the data of s prime and 0 prime, so it's unique. So the conclusion is that the natural number system is an initial counting system in the category of all counting systems where morphisms are defined as translations of counting systems. All right, I feel I maybe rushed a little bit. Does this make sense? You want to ask any questions?
So that is what Dedekind proves?
Yeah, basically the recursion theorem in arithmetic is can be restated as this theorem.
Okay.
Now going back to our fundamental theorem of mathematics, quotation marks. What if, so I've built my category of counting systems, right? I can now define, actually the other way around is also true. So I can begin with taking an arbitrary initial object in this category, and I can prove that it will be the natural number system up to bijection, of course. How can I prove that? Well, I can reverse engineer and I can actually derive mathematical induction out of the recursion principle. But I don't have to. And that is thanks to this theorem that we established earlier, that any two initial objects are isomorphic. So once I already prove one side, that the natural number system is an initial object, and we sketch the proof here. If I have another initial object, then by that theorem, it will be isomorphic to the natural number system. So my proof is done. So it, first of all, simplifies considerably this reverse proof. And then it gives me a fundamental conclusion that really I can think of, by definition, I can really define natural number system as an initial object in the category of counting system. And this is extremely convenient. Why? Because to define a counting system, we didn't impose any conditions. We just had a triple without any further axioms. Even the child's counting system was a valid counting system, right? And now this entire complex, beautiful and complex ideas of Dedekind, which were later adopted by Peano, and today they're called Peano axioms for the natural number system. This axiomatic definition of the natural number system comes out for free as a consequence of the initiality property. So I could literally define a natural number system as an initial object in the category of counting systems and not ever worry about mathematical induction, for instance. And this is a really kind of an example of conceptual simplification that category theory, that looking at things in terms of arrows and in terms of morphisms of structures allows us to arrive at. So I didn't have time now, but in a similar way, we could define the complex number system as an initial object in a certain category, and then afterwards start deriving some properties of it. Of course, we still want to know that a natural number system exists, right? We're not getting rid of constructive mathematics here. We want to know it exists. We will have to build it once to prove that it exists. But once I prove that it exists, I don't have to necessarily use the sometimes complicated construction of my mathematical object, because its construction as a property is equivalent to its definition, which is initiality, and I can just use the property of being initial in this category to prove theorems about the object I'm working with. And mathematicians actually, especially in abstract mathematics, and number theory very soon enters into abstract mathematics as well. As you know, algebraic number theory is what allowed us to prove Fermat's last theorem. There was no elementary proof of that. So a lot of times we want to build very complicated objects in abstract mathematics, and to construct them really is very complicated, but we don't always have to use this construction because we can just use its defining property, and many times this defining property is initiality in a suitable category. So the concept of an initial object is really fundamental, and it's a very interesting phenomenon that in ordinary arithmetic, when we take the category of natural numbers, initial object is just the empty set. So one doesn't really expect too many things out of the empty set, right? But on the other hand, abstracted this way to an arbitrary category, it becomes an extremely fundamental tool for building concepts and building structures. But let me say that even the empty set is important. As we know in set theory, we can create anything out of the empty set. So once you have the empty set, you have a singleton of the empty set, and somebody can build all constructible sets at least from the empty set. So one shouldn't overlook at the importance of nothing. And that's the end of today's lecture.
Thanks a lot. That was very interesting.
Thank you.
Have a nice weekend. Goodbye.
Thank you. You too. Bye.